Hello everyone. In today's video lesson, we learn the subject C programming. For all the computer science subjects, C programming is an initial subject from which we can learn the basics of programming languages. So C programming is introduced in the year 1972 by Dennis Ritchie at Bell AT&T Laboratories. So in previous video lessons, we have learned about history and features of C programming language. So what is actually a programming language? A programming language is a language which communicates an information from the person to the computer. Because the computer is a device, it cannot work on its own. Somebody has to instruct the computer. So we instruct the computer. So the instruction needs to be in some form. So that is nothing but given in the form of programming language. So we had different forms of programming languages: machine language, assembly language, high level language. Machine language allows only zeros and ones. As the computer understands only zeros and ones, machine language is written only in zeros and ones. So everything needs to be written in zeros and ones. So it is a tough job because everything needs to be converted as zeros and ones. But it is very fast because the computer can understand the direct instructions. So it is very fast and efficient. So next, a language called assembly language is introduced. So here, instead of zeros and ones, they have used mnemonics. Mnemonics are used to write the instructions to perform any task. The mnemonics will be like an abbreviations. So it is again a tough job to learn the mnemonics. And here also the assembly language instruction needs to be converted into machine instructions. So a translator called assembler is worked here to convert an assembly language instructions into machine instruction. As it is also a tough job. Next, a new languages called high level languages are introduced. So here we use English-like statements and mathematical notations are used because we are all aware of those things from the childhood. So we are liking it. So this is easy. So here also a translator needs to be worked. So here we use a compiler to convert high level language instructions into machine instructions. So compiler is a translator which converts our high level language instructions into machine instructions. Different types of high level languages are C, C++, Java and so on. So here in this video lesson, I'm going to cover different phases of compiler design, different phases, how the compiler moves on. That means the phases involved in compiler. That means in the form of compilation. And before learning the programs, we'll just see what are the algorithms, pseudocode and flowchart. So let's get into our video lesson. So the first topic, phases of compiler design. So in the phases of compiler design, we have different phases because as the compiler is working, So it has to transform from one state to another state. So compiler operates in various phases because it has to execute. It has to compile the code. So compiler operates in various phases. Each phase transforms the source program. Source program is the program which we write, high-level language instruction. Each phase, there are different phases in compiler, transforms the source program from one representation to another. It will not be like the instruction what we write. If we write C is equal to A plus B, it will not be like the same instruction what we write. We can write an instruction called if A is greater than B. So it cannot be in the same way as we write. It transforms from one representation to another in each phase. And another thing, every phase takes input from its previous stage and feeds its output to the next phase of the compiler. So from first phase, the output will be given as input to the second phase. Next, the output of the second phase will be input to the third phase. Output of the third phase will be input to the fourth phase, and so on. So this will be done in compiler. So let's see the different phases. Lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, code generator. So these are the different phases involved in compilation process. So we have seen in the previous video lesson, Alt F9 and Control F9. Alt F9 to compile our program. And Control F9 for execution of our program. So when you compile, the program goes on, the compilation moves through all these phases. So let's see. So this will be the figure. So you can see here from high level language instruction to assembly code, which will be the executable code. So the high level language will be given as input to the lexical analyzer. Next, the output of lexical analyzer will be input to the syntax analyzer. Output of syntax analyzer will be input to the semantic analyzer. Next, output of semantic analyzer will be the input to the intermediate code generator. Output of intermediate code generator will be input to the code optimizer. Output of code optimizer will be target code generator, and the result will be the assembly code, which is nothing but an exe file, which is ready for execution. So at all the phases, the information, the constants, the functions, the return values, all the addresses of the variables are stored in symbol table. And at all the phases, there may be an error. So a handler will be making some corrective measures so that the errors will be handled properly. So these are the different phases involved in compilation process. So next, so we'll just see what does each phase do. So first is a lexical analyzer. Lexical analyzer divides your instructions into lexemes, which are nothing but we'll name it as tokens. So each instruction is divided into tokens. So they are divided into some different parts. Suppose if you have given some sort of tools, you can divide them into different things. So same way, lexical analyzer will divide your instruction into different tokens by giving some name to them. That means according to their name, they will be divided. So the primary functions of this phase are identify the lexical units in a source code. I have told you source code is nothing but the code which we write for performing some task. So identify the lexical units in a source code. Next, classify the lexical units into classes. That means different items like constants. It can be a constant. In previous video lesson, we have seen in the definition section, we used to give a constant. pi as a constant, definition section. So we can differentiate it as constant, reserved word, and enter them in different tables. You can store them in different tables. It will ignore comments in the source program because the compiler is not bothered about the comments. Comments are always ignored by the compiler. Identify token, which is not a part of the language. If anything is not related to your language, so that will be identified, which is not a part of your language. So next, this is an example. Suppose an instruction is given as x is equal to y plus 10. So here you have two variables, x and y, as they are identified with the names. So they are called as identifiers. So it is divided. Your instruction is divided. You have divided your instruction into lexemes. So what are the lexemes you have? X is an identifier, equal to is an assignment operator because you are assigning the sum of y and 10 is assigned in x. Y is an identifier, plus is an additional operator, and 10 is a number. So you have divided your instruction into different parts. And you have saved it with different names. You have these identifiers, these operators, these numbers, and so on. Like that you have divided. So you have classified your instructions into different items. So this is done in your first phase. Next phase, syntax analyzer. So here I want to tell you an example. So while you are learning your English language, what do you learn? So initially we have learned alphabets A to Z. Then we have learned parts of speech, making a sentence. Using that, we are making a sentence. What do? We write, or we say, Rama is eating an apple. Do we say Rama apple eating? Definitely not. Because we know the grammar says this is the rule. So according to that, we write our instruction. We write the statement. So same way in our programming language also, we have some rules indicating your instructions should be like this. A simple example I'll tell you here. Every C statement must end with semicolon. Like full stop in our English language, every C instruction will be ended up with a semicolon. So it is the syntax. It is the syntax. So if you don't write a semicolon at the end, it will not compile because there is a problem at the second phase. What is the second phase? Syntax analyzer. So we'll just see what does it do. List of tasks performed in this phase. Obtain tokens from the lexical analyzer. Our first phase has divided our instructions into lexemes. Lexemes, which are nothing but the tokens. So checks if the expression is syntactically correct or not. It checks whether the given instruction is perfectly typed or not. Let's have an example. I'll just tell you an example. Suppose C is equal to A plus B. Is it the correct statement? Yes, definitely. We are adding A and B and we are assigning the value of A and B into C. If I write C is equal to AB plus, will you agree? Definitely not. Mathematically, it is not correct. Because the rule says that two operands, in between two operands, you should have an operator so that it will perform some operation. So this statement is wrong. Whereas this statement is right. So it is syntactically correct. So what you have understood here, syntax is nothing but a rule which indicates it should be like this. Rama is eating apple is correct. Rama apple eating is not correct, because we have learned the grammar. Same way we have to learn the syntaxes in the programming language. So in syntax analyzer, it checks the syntaxes. So it checks if the expression is nothing but C equals to A plus B. It's an arithmetic expression. Like that we can have a logical expression. Many expressions we can have. It checks if the expression is syntactically correct or not. Otherwise, report all syntax errors. After compilation, it gives all your syntactical errors. Syntactical errors are nothing but mostly they are all typing mistakes. That is what now example what I have shown you. C equals to A plus B, actually it should be, but what you have typed it? You have typed it as C equals to AB plus. So it reports all your syntax errors. So construct a hierarchical structure. Hierarchical means it looks like a tree, which is known as parse tree. So after checking all the syntaxes, if it is perfect, it prepares an output called parse tree. If the syntax is correct, the output will be the parse tree. So the parse tree is passed to. So what happens in compiler? The output of the first phase will be the input to the next phase. So the parse tree will be the input to the semantic analyzer. So what does it will do? So the work of semantic analyzer is to check the semantics. So what do you mean by semantics? So syntax is a rule which is visible. Like AB plus, you can see that. So it is a typing mistake. So it is syntactically not correct. Syntax is not obeyed there. So whereas the semantic is the logical thing. Though it shows correct, it shows it is correct, but logically it is not correct. Suppose I'll tell you a new thing here, data type in C language. Suppose a variable, a number can hold only integers. Data types are integers and float. You understand only two things here, integers and floats. Integers are the numbers which can hold only real numbers, whereas the floats can hold decimal points also, decimal integers. So if a variable, if a number is indicated that it can hold only integers, if you assign, suppose A is told that A can hold only integers, if you have given it as 2.5, it is not syntax error, because A is equal to 2.5, no problem. It is some value which is assigned to a number. A is equal to 2.5. Syntax error is not there, but there is a semantic error because type of mismatch. Because your A is integer, it cannot hold float values. So in this phase of the compilation, it checks for the semantic errors. That means if there are any logical errors. So functions of semantic analysis phase are, it helps you to store type information. Type information is nothing but the type for every variable, whether it is integer, float, like that, we'll be having different types in programming languages. Gathered and save it in a symbol table or syntax tree. So it gathers the information, what type of value it is, and it is stored at symbol table. Symbol table is nothing but the storage. I have shown you in the figure. So where you can store all the information. Allows you to perform type checking. If it is integer, it holds only integer. If it is float, it holds only float. So semantic analyzer checks the type check. In the case of type mismatch, if there is a type mismatch, if an integer is assigned a float value, where there are no exact type correction rules, we have some mechanisms to convert from one data type to another type. So if you are not using any type correction rules which satisfies the desired operation, a semantic error is shown. If you have not used any correct measure to convert the type, to convert any of the type from one type to another type, so it shows a semantic error. So what are the three things we have learned? One, lexical analyzer, syntax analyzer, semantic analyzer. Simply remember the three things. Lexical analyzer divides the information into lexemes, a smaller words. It can be operator, comma, full stop, semicolon, anything. Smaller things. Next, it checks the syntax, whether the rules are perfectly followed or not. It checks the logical errors. So three phases are finished. Next phase, you can see an example. So here, x is defined as float. That means the value assigned here, it is 20.2. 20.2. It is okay because x is defined as float. It is allowed to write 20.2. Whereas y is with float as well as you are multiplying your x. X is your float, whereas you are multiplying it with integer. So it has to follow some rule, and semantic analyzer will typecast means convert. Typecasting means converting. Typecast the integer 30 to float, which is nothing but 30.0 before multiplication. So it is taking some corrective measures, which is nothing but error handling. Error handling is done here. Right? Next phase, intermediate code generator. It divides your instruction into a simpler task using an address path. So functions on intermediate code generation. It should be generated from the semantic representation of the source program. It takes the input from the semantic representation of the source program because the input is from. So in every phase, it takes an input from the previous output. So it should be generated from the semantic representation of the source program. So it takes the semantic representation, holds the values computed during the process of translation. It holds any intermediate results are available. It helps you to translate the intermediate code into target language. Intermediate code, that means the middle works. For performing an entire expression, you need some simpler tasks in between. So it performs the intermediate code. Allows you to maintain precedence ordering of the source language. Precedence is nothing but the order of evaluation. When you want to evaluate the instruction first, so what do you do first? You make the expression as parenthesized. I'll just write a simple example to you. Suppose C is equal to A into B plus C. This expression will be evaluated from left to right according to associativity rule. Whereas if I want to perform B plus C first, then A, so I will write C is equal to A into parenthesized B plus C. So it gives the highest precedence. The parenthesis gives highest precedence over other operators. So it allows you to maintain the precedence ordering of the source language. So intermediate code generator allows you to maintain the precedence ordering of the source language. It holds the correct number of operands of the instruction. It holds the number of operands involved in your instruction. So let's see an example for this. So I have an instruction, total equals to count plus rate into 5. So intermediate code with the help of address code method. This is done by making use of address code method. So what it is doing, it has taken the address of 5. So actually my 5 is in integer form, but rate will be in the float form. So I want to convert this 5 into float. So at T1, at the address T1, I am converting my 5 into float. So integer to float, it has converted it into float. Next, because the precedence, multiplication has highest precedence over addition in C language. So according to the precedence, rate into T1 is performed. Then it is assigned to T2. Next, T2 is added to count. Next, T3 is assigned to total. So your instruction is generated with your intermediate code. This is nothing but your intermediate code to perform the other activities involved in your instruction. That means simpler tasks involved in your instruction. Next is the code optimization. As the name indicates, it optimizes the code. If you have written the 1000 lines of code, after compilation, it will become a larger one. So to optimize the code is another task of compilation. So what it has to do? So the primary functions of this phase are, it helps you to establish a trade-off between execution and compilation speed. Two things, execution and compilation. So compilation is nothing but Alt F9, execution is nothing but Control F9. Alt F9, execution. Compilation means convert the file into executable code. Whereas the execution, after conversion, this file will be loaded into memory, and after getting all the resources required to it, it will go for execution. So it establishes a trade-off between compilation speed and execution speed. So that is the advantage of code optimization. Improves the running time of the target program. It can execute fastly. Removing unreachable code. Because you have to reduce, if you reduce the set of instructions, then only you can execute very fast. So you can remove some unreachable code which is not used anytime. Suppose if you have written any user-defined programs which are not called at any place, so there is no need of such kind of instructions. So it requires compilation. So it takes some compilation speed. So the time is lapsed over there. So you can remove an unreachable code and getting rid of unused variables. Unused variables are also can be taken away. Next, removing statements which are not altered from the loop, which are not making any alteration in the loop. So you can remove those kind of statements also, which is not altering any loop. So that is called code optimization. You can see an example. So here A is equal to, actually that is into to float. So it is converting your 10 into float. Actually your 10 is in integer form. So in A, you want to assign float value of 10. So actually you want to assign 10.0. So first instruction A is equal to into to float of 10. Next B is equals to C into A. Another instruction E into B. So it is doing 1, 2, 3 like that. So C into A, next E into B, D into F. So this can be optimized. More a set of instructions can be grouped together. So like you can make it as, you can directly assign 10.0 instead of A, finding A. You can find B. So B, A, you can directly find without the first instruction, you can directly find B. And without the third instruction, you can directly find F. F is nothing but E plus B. Actually, D is equals to E plus B, but D is assigned again to F. So directly you can find F. So this is nothing but your 4 lines of code is optimized into 2 lines of code. So this is also the task of compilation. So final one. So this is all ready. The compilation process has done everything. It has been moved syntactically correct, semantically correct, intermediate code is generated, and code is optimized. So you need to allocate the memory to execute. So therefore, all the memory locations and registers are selected and allotted during this phase. Registers are nothing but the storage space, ready to execute place. So the code generated by this phase is executed to take inputs. So that means it is ready for execution. So it is ready to take inputs, whatever we give as an input, and generate expected outputs. Clear? So these are the phases involved in compilation. So that we are ready with the executable file. It will be loaded. That executable file will be loaded into memory, with allowing some of the resources required to the program. We can execute our program. So with this, we'll move further with the next topic, which is nothing but algorithm. Here I am explaining this concept because in the next video lesson, we'll see what is the program, what is the C program, how it will be. So we have learned already, we have told that a program is nothing but a set of instructions which perform some task. So we are telling that it has to follow some instructions. That means we have seen that it has to follow some syntaxes, semantics, and so on. It has to follow some rules. The statements will be like this. So before that, we should have some idea how the program will be, how the program need to be. So a program is nothing but do some work. It's a task. Simply, I have told you, perform an addition of 2 numbers. Or I can tell you an example that, suppose I can give a task to my friend, go and buy some chocolates. It is also a task, but it requires some steps. It needs to be explained to the person. But it is very easier to explain this to my friend, whereas it is some complex thing to explain is explain the same thing to the computer, because everything needs to be formal to the computer and everything needs to be told stepwise, because my friend knows where is the shop and what he has to buy and how it can be, whereas the computer does not know all these things. So everything needs to be explained to the computer. So let's see. An algorithm is a finite set of precise instructions for performing a computation. Computation is nothing but performing a task, or for solving a problem. Computation is nothing but solving a problem. Simply you can say addition of 2 numbers. So you're performing a computation over there. A mathematical problem. You can imagine it's a mathematical problem. So it should be finite and it should be precise, because it cannot be a never-ending story. It should be finite and precise. so that the other person will be understand easily. So for example, directions to somebody's house is an algorithm. So telling it is the address of somebody. So directions to somebody's house is an algorithm. A recipe for cooking a cake is an algorithm because it is also a task. The steps to compute the cosine of 90% is an algorithm. So it's a mathematical problem. So all these comes under algorithm. So for writing any program, the following has to be known. We write a program for this thing. We'll give an input, task to be performed, which is nothing but the process, output expected. We do something for getting a result. So every algorithm will be having input, processes, output. Our computer is also meant for that. We'll give an input, process, get an output. Same way an algorithm is also designed for that. Give an input, task to be performed, mention the task to be performed, get an output. So next, instructions to the computer. A simple example I have given, a simple example without going into the mathematical notation. So in step 1, go to the college board. I'm instructing to my friend. Read the first name. If this is my name, see the rank and come back to check my result. This is an instruction given to the computer. Otherwise, if I want to tell it to my friend, I'll just tell my friend that go and see my result. So he knows how to check the result. So there is no requirement for me to explain each and every step. But the same thing I have to explain to the computer that first step 1, go to the college board, read the first name. If this is my name, see the rank and come back. So the task is finished. If not, if the name is not mine, read the next name. If that is also not my name, repeat the above 2 steps until you find my name. Because the computer does not know what he has to do, what it has to do. So you have to explain everything stepwise. So here the entire task is divided into smaller steps so that the computer can perform it very easily. So the simple task which I can tell to my friend, telling that go and see my result. That is enough for the human, but whereas it has to be told in a stepwise format to the computer. So like this, the algorithms will be. It's just an example I have written to you so that you can understand it better. So let's see an example. So some examples I have given here. Some algorithms are harder than others. Some algorithms are easy, like finding the largest value in a list. Suppose if you have 5 elements, you can find the largest value, which we call it as sorting or searching. Sort the elements, you can find the largest or the smallest, and you can search the element which is the largest. Finding a specific value in a list, so which is nothing but the search. Some algorithms are a bit harder, like sorting a list. As I've told you, sorting means making the elements in an ascending order or descending order. Some algorithms are very hard, like finding the shortest path between Miami and Seattle, some place. Okay. Some algorithms are essentially impossible, a complex task, like factoring large composite numbers. So these are the different types of algorithms we can see. So I have just given an example of addition of 2 numbers. So first we have to give an input. So start, declare variables number 1, number 2 and sum. You can directly take 2 variables which are nothing but number 1 and number 2. And the third one is the sum, where you want to store the result of number 1 and number 2. Addition of 2 numbers. So read values number 1 and number 2. First indicate there are 3 variables with which you are working. So take number 1 and number 2. At both step, what do? Add number 1 and number 2 and assign the results to sum. So which is written like this, number 1 plus number 2 and assign the results to sum. So this is the process. Reading the values and addition is the process. Task to be performed. So it is an input. Reading the values is an input. This is the task to be performed. Display the sum is an expected output. So stop. So this is nothing but the stepwise indication of your program. Right? So next, characteristics of an algorithm. Our algorithm should be finiteness. It should be finite. In the definition also, we have seen that the instructions should be finite. An algorithm must always terminate after a finite number of steps. It should not be never ending. After finite number of steps, it should be ended. Next, definiteness. Each step of an algorithm must be precisely defined. It should be precise. Next, input. An algorithm has 0 or more inputs. Without input also the program can be. You do this. So we don't give anything, but he has to print something onto the screen. So that is without any input also, output. An algorithm has 1 or more outputs. So definitely every program will be displaying 1 output, or it can display more than 1 output also. Effectiveness. Each step must be effective. Each instruction. We write everything in a step. So each step must be effective. That is, it should be convertible into program statements and can be performed in a finite amount of time. That means each instruction must be effective. Right? Next, flowcharts. Flowcharting is a diagrammatic representation of an algorithm. We have seen just all the statements in a stepwise instruction. So here the stepwise instructions are shown as diagrams. So it is made up of boxes, diamonds and other shapes connected by arrows. From one step to another step, we connect it by arrows. Each shape represents a step in the process. Each shape represents different processes. And the other arrow shows the order in which they occur. From where to where. It shows the flow from one box to another box. Each box represents some process. Whether it is an input, whether it is an output, whether it is an execution phase, what it is doing. So each step is shown in different boxes, and each box is connected with the flowchart with an arrow. So flowcharting combines symbols and flow lines. Symbols are nothing but the boxes, and flow lines are nothing but the arrows to show figuratively the operation of an algorithm. So simply an algorithm is shown as a flowchart. So here a box, a rectangle is represented as a process. A parallelogram is represented as an input output, whereas the rhombus, we call it as diamond shape, also used for decision. A circle for connector. A double-ended rectangle is used to write subroutine or an interrupt program. Interrupt means something which stops execution of our program. And terminal is nothing but start and stop. In an algorithm, we have seen the step 1 is start, last step is stop. So we use an ellipse, terminal. This symbol we call it as ellipse. So we call it as terminal. And we will be having flow lines like this. So this is used to execution thing. For execution, we use this box. That is, if you want to C equals to A plus B, that will be done here. The processing task to be performed. This is used to take an input or print an output. This is used to decide if you want to check if whether A is greater than B. So whether you want to go for the this part or this part. If it is true, go for the first part, or if it is false, you go with the second part. So decision. Connectors, if your flowchart is bigger, connecting from one page to another page, you use the connector. Subroutines and interrupts you may not be having in every program. Subroutines are nothing but the other subprograms, and the interrupts are nothing but the which disrupts or which suspends your process under execution. And the terminal start stop is used to written with the terminal symbol, which we also call it as ellipse. And flow lines, which are nothing but the arrows, are used to connect from one box to another box. So this is an example. So start and stop are shown as terminals, ellipses. So this is an input, get the sum. This is the process, rectangle, where you are performing an average equals to sum divided by 6, and this is an output. So it's a simple flow chart which explains the stepwise instruction into a diagrammatic representation. So each box, your ellipse, your parallelogram, your rectangle, your parallelogram, and your terminal are all connected with flow lines. So this is called flow chart. Right? Next and the last topic is the pseudocode. It also simply looks like an algorithm. Only the difference is it also represents the instructions in a steps. That means it just writes what you have to do. Go there, come here, do this, like that. But only thing is the instructions which you write in pseudocode cannot be convertible into any programming language. So it is simple like our own language. It does not sound in a programming language way. So it's a pseudocode. Okay. So pseudocode is a generic way of describing an algorithm without use of any specific programming language syntax. It does not follow any syntax of any programming language. It just writes what to do without following any syntax. So it is, as the name suggests, pseudocode. It cannot be executed on a real computer. It cannot be converted into any of the programming language, but it models and resembles real programming code. It just writes like it shows a programming language. Do this, take the input, do this, give an output. But it does not follow any kind of syntaxes. So it is similar like an algorithm, whereas the algorithmic steps are convertible into programming instructions because they follow some syntaxes of programming languages, whereas the pseudocode does not follow any syntax. So simple example I have taken: start, get the sum. It's an input, average equals to sum divided by 6. It's a process. Output the average, stop. Output the average. Actually, the stop should come down. I am not saying. So it's also an instruction which tells what to do, but it is not exactly convertible into programming instructions. So this is all about today's video lesson. So hope you have understood what I have explained today. So we'll meet in the next video lesson for C programming. Thank you for watching.